Okay, all right. Let us start. Let us start today's session. So, I'm Prithvi. I'm a PhD scholar from IIT Hyderabad. So, in today's session, we'll be solving few questions on the again the on some concepts on the force concepts on the force method. So, in the last session, if you have attended or if you have watched the video link. You might have noticed that in the last session we have solved questions of so we have analyzed statical indeterminate trusses, and in this session we will solve questions on statically indeterminate beams and frames. Okay, so I'll take some. I'll start with beam problems, and then we'll solve a couple of beams, and then we'll go ahead and solve some frame problems so that the concepts will be clear, and also it will fetch you, and it will give some idea for you to solve questions which are there in the assignments. So let us start the session. So first question, let us take uh, a beam. So this is a fixed beam. Okay, so we have a fixed beam which was loaded only up to L by 2, half the span. Okay, so this is 10 kilonewton per meter UDL up to half the span. So the distances are 10 meters, 10 meters. Okay, so now solve for the support reactions, draw bending moment area, BMDs, and also SFDs. So support reactions, BMDs, and shear force diagrams. Okay, fine. First, let us understand uh, whether this beam is an indeterminate or a determinate structure. Okay, so how do we know whether it's indeterminate or indeterminate? Let us go from the basics. This is a fixed beam. Okay, so for the fixed beam, usually at this fixity you have two unknown reactions. One is the vertical shear force and also the bending moment. Similarly, on the other end you have the same vertical reaction and also uh, the bending moment. So we have two unknowns at one support and two unknowns at another support. So we have total unknowns are four, and equilibrium equations, we have only two equilibrium equations. One is sigma Fy equal to 0 and sigma m equal to 0. So you may ask me what about sigma Fx? Okay, so in this, as it is beam, we usually consider the gravity loads. For in case you have some inclined load, something like this, let us say you have some load like this P. So in this case you also have an extra reaction at each supports. Okay, you'll also have horizontal reactions at this support. But as we are discussing about the vertical loads, which are the gravity loads, the loads which are acting vertically or which are acting transverse to the members, so in that case we'll just ignore these horizontal forces. All right, so we are ignoring these horizontal forces. So we have only two equilibrium equations. One is Fy equal to 0 and sigma m equal to 0. So when it comes to the static indeterminacy, that is 4 minus 2, 2. This ds equal to 2, which represents that we need two extra equations in addition to the equilibrium equations to solve for the support reactions. Okay, so so yeah, it is indeterminate structure. It is a fixed beam. So we have two fixed supports. The degree of static indeterminacy is 2. So we need two extra equations to support. So what is our process? So what is our procedure before? So as we learned, we need to actually we need to kind of bifurcate this beam into two into two, or in this case three different beams. So what we'll try to do is, we have this initial beam. So what I'm assuming is, I'm assuming the redundant force at one as the shear force at support B, and the bending moment at support B. Okay, I'm assuming P and M as my unknowns. Okay, so what I'll do is, this is my initial beam. Okay, so initial beam, I have removed the redundant forces, so I don't know P, I don't know M. So this will be a cantilever beam. Now I have converted, I have actually made this fixed beam to a uh, determinate beam, which is a cantilever. Plus, now what I'll do is, I'll just add P in this direction. Okay, this is my unknown P. Plus, also I also have M, which is unknown. Okay, fine, we have done this. But what is the purpose of doing this? So, if you ask me what is the purpose of doing this, let me name this as A, B. This is A, B, and A, B. Okay. So the purpose of doing this is, so at support B, now we need to understand what is happening at support B. Actually, for the indeterminate structure, that is a fixed support. What is happening at this location? At support B, if it is fixed, that means the rotation is zero there, right? There will not be any rotation there. So theta B should be zero. Okay, that is one condition. And what is the second condition? At support B, the displacement should be zero. Okay, so it should not displace. Okay, so delta B is equal to zero. So these are the conditions. Okay, these are the conditions by which we try to develop, or we try to find out the unknown forces P and M in this for this kind of a problem. So for theta B equal to zero, now we have three different beams. One, let me call this as beam one, beam two, beam three. The same beam, right now what we have done is, we have actually divided into three different beams. One as a cantilever with the given load, that is 10 kilonewton meter. The other one is the cantilever beam with unknown force P, okay, the support reaction P, plus the cantilever beam with unknown bending moment at support B, M. Okay, so in all these cases, when if you add the slopes, okay, let us say theta at B because of 1. Okay, I'm writing it as 1. So what is 1 is actually the theta. This is 1, this is 2, this is 3. Okay, theta at B because of in the beam 1, plus theta at B in beam 2, plus theta at B in beam C in 3 is equal to 0. That is condition number 1. Okay, now what about the second one? Delta 1 excuse me, delta 1 at B plus delta 2 at B plus delta 3 at B is equal to 3. This is my second equation. Okay, now how do we find theta 1, theta 2, theta 3? Right now the beam 1, beam 2, beam 3 are the determinate structures, right? So for the determinate structures, we already know how to find out the slopes and also the displacements. Okay, so let me take beam 1. You can stop me in between if you have any doubts.
Yes,
I'm
sir.
assuming, yeah, I'm assuming that you are, yeah, sure, thanks. So beam 1, let us take the beam, cantilever beam. This is my cantilever beam with external load 10 kilonewton per meter. Okay, this is my beam 1, this is A, this is B. So what is theta 1? Theta 1 is nothing but theta at B. in this. So how do we find the theta 1? So we have moment area. Let us use moment area method, which is which by which we can easily solve our slopes and also the displacements for the cantilever beam. So this is 10 kilonewton meter. So what is the force here? 10 times this is 10, right? This is also 10. So this is 10 meters and this is 10 meters. So my vertical reaction will be 10 in 10 times 10, that is 100 kilonewton uh, upwards. And also whatever the moment, 10 times 10, that is 100, which is acting here. 100 times 5, this is 5. So this is 500. This is going to be in this direction. Sorry, not in this. This is going to be in this direction. 500 kilonewton meter. So we have solved for the support reactions. Now how do we use the moment area method? So we have, let me draw. So we have let me draw the bending moment diagram. So at support A we have 500 kilonewton meter, and somewhere in the middle the bending moment should be 0, and at this span the bending moments are 0. BMD is 0. Okay, I mean BM, bending moment is 0. So how do we draw this? So I'll be having something like this. Okay, this is a parabolic. Why is it parabolic? We have a UDL. Okay, it's a
Yes,
UDL.
sir.
So you have x square as a this x square as your bending moment equation, and that is why it will be a parabolic. And why is it touching like this? Why is it tangential here? So I'll just explain why is it. It can also be something like this. It can also be something like this. This is also a parabolic. So why is it touching like this? Let me just clear that out. So one thing is you can directly find out what is happening at each point, what is happening at each point, and you can just plot whether if it is coming above, that means if it is more than your half. So let us say if this is a straight line. So if it is more than that, more than what you are getting at the straight line, then it is uh, this is called convex, right? Something like this, convex. If it is not more than that, if it is lesser than that, then you'll be have a concave. Otherwise, also you have an easy method to judge whether your bending moment diagram is concave, something like this or something like this. So I'll just tell you how to actually find how to actually judge how your bending moment diagram is. So see what happens in this case is, let us say this blue one. So this blue one, right? So what happens? You just check what is happening at this point, which is mid span. This point, what is shear force in this span? At that span, the shear force is 0, right? So you don't have any load in this span. So the shear force is 0. So shear force is nothing but dm by dx. The slope of bending moment diagram will give you the shear force at that point. Okay. So if dm by dx is 0 at that place, that means the tangent of your bending moment diagram should be 0. Okay. If you draw a tangent, the bending moment for the bending moment diagram, it should be 0. So that is only possible if your bending moment diagram is uh, something like this, the blue one. For the red one, what happens to the red one? If the bend moment diagram is also, again, you can there is a possibility of being like this. So for the red one, you have some tangent, right? There is some tangent here. But for the blue one, you don't have a tangent. Tangent is 0. Tangent is nothing but tan theta. Okay. So tangent is
Yes,
0.
sir.
So that is how you need to judge how your bend moment diagram is going to be. So yeah. Anyways, this is my bend moment diagram. And how much is this? This is 500, and this length is going to be 10 meters, and this is 10 meters. So I don't have any bending moment in the span. Let me just name it let me just name it as C. So I don't have any bending moment in CB. Okay. So how do we find the slope at B? So that's the question. So how do we find the slope at B? So let me just draw the deformed shape. So I have a cantilever, I have a load here, and this is B, this is C, this is A. So how is my deformed shape is? So the deformed shapes is something like this. So there is non-linearity. In CB there is no bending moment, right? So if there is no bending moment, the beam is not going to have any curvature in it. So it is just going to be a straight line. It will be a straight line like this. Okay. So now what is theta C? Sorry, theta B is nothing but the slope. This is my theta B. This is what we need to find. This theta b is not. If it is straight line, what does it mean? Straight line has slope equal everywhere, right? So you can just simplify. This is theta b. Okay. So this is my theta b. How do you find theta b using using what is it called? Using moment area method. Theta b is nothing but the area in between the area in between the point of interest to the tangent where the to the tangent where the slope is zero, right? So you know the slope at this point is zero because it is a fixed support. The slope at theta a is zero. So you need to just find the area of bending moment diagram in between A and C. So we already have. So this is the if you find this area that gives us what is directly the theta b is. So theta b is nothing but theta b can be written as. Now what is the area of such a parabolic curve? So the area of such a parabolic curve is 1 by 3 times 500. So 1 by 3. Okay. So what I'm trying to say is this is 1 by 3 times this rectangular area. This is 1 by 3 times that rectangular area. So that is 1 by 3 times 500 times 10. Okay, 500 times 10 divided by EI. Don't forget this. So this is EI. It is always M by EI diagram. It's not exactly the bending moment diagram. It is M by EI diagram. So from this, what we are going to get is 5000 by 3 EI. So what did we name theta b as? Theta b is nothing but theta 1. So theta 1 in our equation. Theta 1 we have found it as 5000 by 3 EI. Okay, this is about theta 1. What about delta 1? Delta 1 is nothing but the deflection at the at the end of the cantilever beam, that is at B. So this is my delta 1. So how do we find this delta 1? Initially we can find this, let us call it as delta 1 or delta 1 delta C, let us call this as delta C, and we let us say this is let us call it as delta C C dash. Okay. So how can we delta 1 is how much? That is the thing. This is nothing but delta 1 is nothing but delta C plus delta C dash. So how do we find delta C? So it is again using BMD we can find delta C. Delta C is nothing but the moment of the area of bending moment diagram about the point C. Okay, about the point C, the moment of the bending moment BMD diagram. So delta C is going to be again what is the area? 1 by 3 500 times 10 by EI. Now tell me what is the centroid for such a. Now what is the distance of this centroid? This
2 by
distance
3.
is sorry. Can you repeat?
So 2 by 3 from here. 2 by 3 times 10.
No, no. That is for the triangular shape. This is not the triangular shape, right? This is parabolic. So for the parabolic, it will be 3 by 4.
Yes,
Okay.
sir.
Yeah. For the parabolic, I'll just maybe it will be helpful. So what I so let me note down. So we have this line, and let me say this is a triangle. Yeah. So Okay, this is one parabola. This is another parabola. Sorry, this is another parabola. Okay, and we also have, let us say, a rectangle. Yeah. So let me note down. Let me write down what all. What is the distance of the centroid? So we have this. Let us say this is A. Let us say this is A, side A, and let us say this is B. Okay. So now for this area, actually this is what we are doing now. Okay. For this area, I'm writing it as area 1. Okay. Area 1 is nothing but 1 by 3 times A into B. Okay. This is area 1. Now let us say area 2. Area 2 is nothing. Area 2 is this complete triangular area. Okay. So area 2 is nothing but, you're right, half A times B. This is triangular area. Okay. Now what about area 3? So this is my area 3. Let me, how should I write? I'm just making some dots. Okay. So this is my area 3, which is in the black. Uh, this complete area. Okay. This complete area is my area 3. Yeah. So area 3 is nothing but 2/3 of AB. Okay. And the rectangular area, I hope you know, A4 is nothing but A times B. Okay. Now, uh, now for A1 is nothing but this. Let me, yeah. For A1, now the distance, I'll just draw it here. Now this is my A1. Okay. So for A1, this is B, this is A. This is a parabola, right? So for A1, the distance of the centroid, so let us say the centroidal distance is somewhere here. This is 3 by 4 of A, and this will be 1/4 of A. Okay. And if you have a parabola in this is also another parabola. When your parabola is a convex type of a parabola, in this case, this is going to be, sorry, 5 by 8A, and this is going to be 3 by 8A. Okay. And if you, again, like you said, if you have a triangular variation, so if your BMD is a triangle, so then if this is B and this is A, how much is this?
2/3.
2/3. Yes, you're right. So this is 2/3. Okay. You better make a note of this and keep this in your mind, because every time when you're doing this BMD calculations, right? Most of the
Yes, sir.
students make mistake while taking this centroidal distance. So in our question right now, we need to take 3 by 4. Okay. So 3 by 4 of A here is 10. So 3 by 4 of 10. So delta C is going to be, I'll just 5,000, 3 knocks off 5,000 times 10 is 50,000 by 4. It's 12,500. This is going to be 12,500 by EI. Now, what about delta C prime? Delta C prime. How do we find delta C prime? So, delta C prime can be found out by, we already have theta B. Okay, we have theta B. So, tan theta B is nothing but delta C prime by 10. This is 10. This is 10. So, I'll just write it here. Tan theta is equal to delta C prime, opposite side, by adjacent side, that is 10 meters. So in the structural analysis, like whatever we are dealing with, right? So in structural analysis problem, always we deal with uh, a very small deformations or very small displacements or very small slopes. So tan theta b can be approximated as theta b. So theta b, tan theta b is not is approximately equal to theta b. So delta c by 10. So delta c prime will be theta b times 10. Okay. Delta c prime is theta b times 10. And what is theta b? It is 5000 times 10 is 50,000 by 3 ei. So with this we have found out delta 1, that is nothing but delta c plus delta c prime, and that is going to be 12,500 plus 5,000 50,000 by 3, and that is going to be 87,000. Let me write it down. 12,500 by ei plus 50,000 by 3 ei. So delta 1 is going to be 87,500 by 3 ei. Alright. So this is my delta 1. I have finished calculating theta 1 and delta 1. Now my beam 1 is over. This beam 1 is over. Okay, I have calculated my theta in this. Now let us go to beam B, beam 2. This is my beam 2. Okay, so the same process again. We need to beam 2. So we have cantilever, and in this we have a redundant force P which is acting at the support B. Okay, so the redundant force P which is acting at support B. Uh, Again, how let us draw the bending moment diagram. Initially, let us know what are the support reactions. So if this is P, we have downwards P, and what about bending moment at support A? P times 20 is 20P in the clockwise, so it should be in anti-clock. It should be in clockwise direction, 20P. Okay. So now bending moment diagram. Okay, I'm just trying to draw the bending moment diagram. So my bending moment will be 20P, and this is triangular. Sorry, let me just. This is going to be triangular. All right. So here it is 20. Oops. Yeah. Yeah. Here it is going to be 20. This is going to be 20P, and the length is 20 meters, as we already know. Okay. Now what is theta 2? Theta 2 is nothing but theta B. Displacement at B, A, B. So displacement, sorry, slope at B. So theta B is nothing but half area of the bending moment area diagram, right? Bending moment, I mean M by EI diagram. Half 20 times 20P by EI. So this is going to be 10. Theta B is going to be 200P by EI. That is going to be theta 2. So theta 2 is 200P by EI. Okay. What about delta 2? So delta 2 is nothing but delta at B. How do you find delta 2? Delta 2 is moment of the area about B. Okay. So what is the moment of the area about B? Half times 20 times 20P by EI is my area. Now what should be the centroid? Tatik?
Two-third of 20.
Yes, 2/3 of 20. So this is going to be for 8,000 by 3 EI. Yeah. So this is going to be 8,000 by EI. So we have obtained theta 2 and delta 2. Now what's our next target? Our next target is to find for beam 3. So beam 3. Let me just recap what we So yeah, this is my beam 3. Okay. Yeah, this is my beam 3. Beam 3 is having, it's a cantilever with moment M at the end. So we have a beam, cantilever beam, moment M acting. So what are the support reactions? Do we have any vertical reactions at A? No, no,
No,
right?
sir.
We'll not have any vertical reactions at A here. So we'll only have bending moment M, which is opposite at this. So the bending moment diagram will be a simple box. It's a rectangle. So we have M by EI. So theta 3 is nothing but theta at B, A, B. That is nothing but area of the bending moment diagram. M by EI times 20. That is 20 M by EI. This is my theta 3. What about delta 3? Delta 3 is nothing but the moment of the bending moment area diagram uh, at B. Okay. So that is going to be M by EI times 20 times 10. That is 200 M by EI. Okay, these are theta 3 and delta 3 values. So now the sign convention comes into the picture. Okay, so now we need to be very careful while we are using the when we are using the sign. So tell me for the beam 1, the theta, how is the displacement? Displacement will be to downwards or upwards for beam 1,
Downwards. Downwards.
right? Yeah, what about for beam 2?
Beam 2, sir, upward.
Upwards. What about 3?
3, sir, down, upward.
Upwards, right? You're right. So in that case, what happens is that when you are doing the algebraic sum, right? So that means the theta 1 should be equal to theta 2 plus theta 3. This is 1. And delta 1 should be equal to delta 2 plus delta 3. Okay, because we have taken downwards as positive. Let us say if the downwards as positive, that means delta 1 minus delta 2 minus delta 3 equal to 0. So I'm just taking delta 2 and delta 3 to the right hand side. So delta 1, so because of the displacement, because of delta 1 should be negated by the displacements in because of delta 2 and delta 3. Okay, so this is our I'll just repeat what I've said. So in this, okay, in this what I've assumed is all the displacements which are downwards are positive. Okay, but my delta 2 and my delta 3 are actually upwards. So that means I should be writing as delta 1 minus delta 2 minus delta 3 equal to 0. So I've just taken it to the right side, and delta 1 is equal to delta 2 plus delta 3.
Yes, sir.
Similarly, yeah, similarly the rotations also, right? So theta 1, so I'll just say how the rotations are. So let us say for my beam 1, this is my beam 1. You have a displacement, you have a loading like this, and this is my beam 2, upward loading, and you have a beam 3, moment is, you have a uh, anti-clockwise moment. So in this, how is this going to deform? In this is going to deform like this, and here you have a straight line. So in this, how this is going to be deformed? So this is going to deform like this, and in this, how this is going to be deformed? This is going to be deformed like this. So what is my theta? So theta is something this. This is my this is my theta. What about this? This is my theta. Okay. What about this? This is my theta. So theta 1, let us say this is clockwise, it is clockwise, here it is anti-clockwise, and here it is anti-clockwise. That is the reason
Yes,
why
sir.
I'm taking yeah, that is the reason why I'm taking theta 1 is equal to theta 2 plus theta 3. Okay, so yeah, now we already have delta 1, delta 2, delta 3, theta 1, theta 2, theta 3. Let me just plug into this equation. Okay, so theta 1, what is theta 1? Theta 1 is 5000 by 3 EI. So 5000 by 3 EI is equal to, what is theta 2? Theta 2 is 200 P by EI. 200 p by ei. What is theta 3? Theta 3 is 200, sorry, 20 m. 20 m by ei. This is equation 1. And what about delta 1? Delta 1 is 87,500 by 3. 87,500 by 3 ei. That is nothing but delta 2. What is delta 2? 8,000 by 3 ei. 8,000 by 3 ei into p plus, what is delta 3? 200 m by ei. 200 m by ei. So if you solve this, we have two equations, two unknowns, p and m. If we solve this, we'll get what is p and what is m. So those are the redundant forces, and once we solve for the redundant forces, now we can find the other two forces. So Pratik, can you quickly solve this equation and tell me what are the answers?
Yes, sir.
If you have a calci, just 2 minutes. Okay.
Yes, sir. So now I don't have a Kelsey.
Okay. Fine. Fine. Okay. I have just solved it. I'll just tell you. I'm just a second.
Yes, sir.
So the answer is P is going to be 18.75 kilonewtons. After this session, you can verify. Okay, 18.75 kilonewtons,
Yes, sir. That.
and M is going to be minus 104.17 kilonewton meter. Okay, this is what I'll be getting if I'm going to solve the equations 1 and 2. So now what okay, P is positive. So positive means whatever I have assumed initially, which is upwards, and I'll be getting it as upwards. What does M negative refer to? M negative refers to my initially I have assumed it to be in anti-clockwise direction, but now right
Yes, sir.
now, yeah, right now it is going to be clockwise. Okay, I'll just so this is one equation. This is my question, initial question. Now what I have obtained is this is 18.75, and this is going to be 104.17 kilonewton meter. Now I have right now I already know these two support reactions. Now I need to find this support reaction and also this. So how do you find this? Instead of calling this, I'll just say this is RAMA. So RA plus 18.75 is nothing but 10 times this is 100. 10, 10. So 10 times 10. So 100 minus 18.75. R is going to be, is it 82? 81.25 kilonewton. Okay. And MA you can simply find out. So how do you find MA? MA MA is going to be
Zero.
10. How is it 0?
Sorry, sir. Zero summation वो moment calculate करेंगे इसका.
Yes, yeah. Sigma MA is 0. Yeah. So MA, let me write it here. So somewhere. So we have MA. Is it clockwise, right? Let me take clockwise positive. MA plus, this is also clockwise, 18.75 times 20 minus 104.5, sorry, 17 minus 10 times 10 times 5. Okay, this is going to be 0. So if you solve this, you'll be getting Okay, I need to solve this. I think. Yeah. So if you solve this, you have 18.75 is because of the support reaction at B. So that is going to give you a anti-clockwise moment. Minus 104.17 is the support reaction at B, and we have because of the UDL, which is 10 kilonewton meter, that is 10 times 10 is the total load, and the 5 is the distance of the centroid. So this is going to be 229.17. 229.17. This is plus, yeah, kilonewton meter. Okay. So now I'll just no, write down my complete solution here. So this is my support. This is my fixed support. I have a UDL of 10 kilonewton meter acting. Okay. So my support reactions over here is 18.75, and here it is 81.25. 9 and 9, yeah, 81.25, and here it is 229.17.
229.17.
Yeah, 229.17 kilonewton meter, and this is going to be 104.17 kilonewton meter. So now we have obtained the support reaction. That is what the question asked for, right? That is what we are asked for. So how do we find the shear force diagram? So shear force diagram, let me just plot directly. So we have, this is my line, okay, baseline, and at support A I have 81.25. Okay, this is my shear force at support A, and at the C, what is going to happen? At C, 81.25 minus 100, that is going to be minus 18.75. So at C, it is going to come downwards. And how am I going to join this? This should be a straight line.
Yes, sir.
Okay, this is my straight line, and in this is A, this is B, and this is C. In CB, do I have any shear force, extra shear force in CB?
Yes, yes, sir.
In
18
C,
point 18.75.
right, you are right, you are right. So that is going to be constant, and again at support B, it is going to be zero. Exact. I mean, just in the right of the support, there's no shear force. So this is my shear force. Okay. So it is 81. 81.25, and this is minus 18.75, and this is zero. All right. So positive, and this is negative. So this is about my shear force diagram. Now how is my bending moment diagram going to be? So I'll just draw baseline again. This is my span. So what is happening at A? At A, I have a hogging bending moment of 229.17. So if it is hogging, uh, yeah. So let it is negative. Okay, hogging, I assume it as negative. So this is 229.17. And what about at B? Oh, at B it is again 104.17. Anyways, I'll come to that point in a few seconds. So what is happening at C? Let me just calculate my bending moment at C. Bending moment at C is nothing but minus 229.17, 9.17, okay, plus 81.25 times 10, okay, minus 10 times 10 times 5. So this is my bending moment at C. So that is going to be minus 229.17 plus 81.25 times 10 minus, that is going to be 83.33, which is positive. 83.33 kilonewton meter. Okay, so at this support it is going to be 83.33. Now how is it going to uh, how is it going to, so let me just draw it here. Okay,
Parabolic.
yeah, it is going to be parabolic, yes. And yeah, 83.33. And we also have, is it going to be at midspan, or is it going to go down, or is it going to go up?
Sir, down.
Yeah, because it's already positive, right?
Yes,
That's what
sir.
it means. So it's already positive, so it is going to be down. So let me just note. Yeah, this is my point. Let me say it's my point. So this is going to be parabolic, something like this. Okay. So now we can't say the shear force is zero because we already have some shear force at C. So you can't. I'm just writing it. I'll just mention it as 2-degree parabola. Okay.
Yes.
So yeah, what is going to happen at B? At B. So at B it is again negative, right?
Yes, sir.
So at B it is again negative. That means it is going to go upwards again. So how can you write that? So minus 229.17. So just let me. Otherwise, what I'll do is, like, just to avoid some confusion. Let me take the bending moment at distance 15 meters. Okay, so I'll just write the bending moment diagram, the bending moment equation. So bending moment, I'll call this as D. Bending moment at D. Now I can use this right side support also, right? So right side support I'll be using. So my right side support is actually trying to bend the beam in minus 104.17, but plus 18.75 times 5. So this is going to be minus 104.17 plus 18.75 times 5. So this is going to be minus 10.42. So this is going to be minus 10.42. Okay, let us say this is my that point. So what is going to happen at B? What is going to happen at B? Is it going to be minus or plus at B?
Plus, sir. Plus.
No, B is hogging, right? So it is going to be
Yes,
minus.
sir.
So I'll just tell you. I'll just tell you what is going to happen. So you see at A, is it hogging or sagging at A?
Hogging.
Yeah, it is hogging. What about at B?
D, sir, also hogging.
Yeah. So you know the sign convention, right? Like for example, if this is a B,
Yes, sir.
what is this?
Hogging.
Yeah. What is this?
Sagging, sir.
Yeah. So right now our condition is the first one, right? This is something like this. So if towards the right side, if it is in clockwise direction, then it is hogging, right? So
Yes, sir.
now what is going to happen is it is going to move in this direction. So this is 229. This is
Yes, sir.
229.17, and this is going to be 104, which is again minus. So this is going to be something like, this is 104.17, and this is going to be straight line.
Yes, sir. I'm saying this, but I'm just confused that positive is negative now.
Okay, now you are able to
Yes, sir.
yeah. So this is negative and this is positive. So yeah, so this is what the question is about. So maybe maybe you will be also asked, what is the point of contraflexure?
Yes, sir. Where the moment, moment sign changes,
Correct, you are
changes the
absolutely
sign
right.
of moment.
You are
Bending
absolutely
moment.
right. So that, yeah, that is called point of contraflex. So how many point of contraflexures we have in this?
Two, two, sir.
Two. Yes. So this is one and this is two. So maybe in the question they'll be asking you what is the point of contraflexure. So you need to just make so in this section now. Let us say in AC, you make x. You just assume some x distance and then you equate it to zero and you can find out the point of contraflexure. Okay.
Yes, sir.
So let me just write it down for you. So let us say I have the point of contraflexure is at distance x from support A. So bending moment Bm at x is going to be minus 229.17 plus 81.25 into x. Okay, minus 10
10 x
times
square.
x. Yes,
X, y.
yes, yeah, yeah, by 2, that is equal to 0. So minus 2 point x plus 81.25x minus 5x square equal to 0. If you solve this parabola, solve this parabolic equation, let me solve this. Yeah. So minus 5, 81.25 minus 229.17. 81.25 and C is going to be, how much is C? Minus 229.17. So X is going to be, yeah. So X is going to be 3.63 meters, and also there is one more X, so you need to be 12.61 meters. Okay. So if it is 12.61, right? So 12.61 cannot be the answer. So can you tell me why?
Sir, because here is positive bending moment, we can
Right.
say in the diagram.
Yes. Yeah. 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 So see, we are actually considering only up to this 10x only. This 10 meters first span, right? So the
Yes, sir.
maximum value of x can be only 3.63, not more than 10.
Yes, sir.
You understand? So, sir, the maximum value of x can be 10, not more than that, because we are only
Yes, sir.
considering AC. So this point will be 3.63 meters, and the other one will not be. The other one will be the other one. How can you find the other one? Other one is quite straightforward. You need to just find out. Let us say this from support D. Okay, sorry, support B. Now I'll just write down BM, bending moment at. I'll say this as Y. Okay, this distance as Y. Bending moment at Y is going to be minus 104.17 plus 18.75 times
18.75 x.
x is equal. Yeah. So this is going to be 104.17 divided by 18.75. 5.55. Okay. So this is by 5.55 meters. So this is 5.55 meters. Okay. So this is all about the first question. So we were given a fixed support. We had loading in only the half span of the support. We tried to find out the support reactions using the flexibility method or the force method. What we have done is we have actually bifurcated we have divided the beam into different uh, determinate structures. So by doing so, we have used the compatibility conditions by saying that wherever the redundant forces are coming, right? So in that at that redundancy, we have zero slope and we have a zero displacement. So by that we have developed the displacements and slope equations. We have added them, and then we have found the redundant forces P and M, and then we have drawn the shear force diagram and also the bending moment diagram, and also we have found out the 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 distance or the points of contraflections. Okay, this is about the question one. Do you have any doubts in this? Shall we move to the second one?
No, sir.
Yeah. So let us solve the next question. So this is also similar question. Maybe this is more simpler than the first question. So So we have a cantilever beam. It's a cantilever beam, but we have a spring support. Okay, this is a cantilever beam. We have a spring support. Okay. So this is a spring support. At the spring support, we have a load. We have a load of say five. Is it five? Five is very small. Let us take. Let us take 50. 50 Newton acting, and this is A, B. So if it is a spring, we also have the stiffness of the spring, right? K is equal to stiffness is given as 2 Newton per mm, and the beam, the cross section of the beam is also given. So AB, the cross section is a rectangular cross section, 10 10 mm deep and 5 mm wide. Okay, so this is basically not a very civil engineering structure. This is kind of a mechanical structure, maybe a very small structure which is carrying only a 50 newtons of the load. Okay, so now first tell me whether it is a determinate structure or indeterminate structure. So if you see now again the only thing is you need to draw the free body diagram. So in this support we have two unknown forces, and at support B we have three. At support B we have one unknown forces. So we have unknowns are three. Let us say this is R A, reaction at A, moment at A, and R B three. And equations. How many equations we have? Equilibrium equations we
Two.
have only two. Yeah, you're right. So ds is going to be 3 minus 2, that is 1. So it is statically indeterminate with a redundancy of 1. So like we have done previously, we'll just bifurcate this beam or divide this question into two simpler questions. So one is with 50 newtons acting, plus one is the reaction in the spring, which is RB. Okay, so you might be thinking what is going to happen here, right? So if for example, if in the spring there is some force, so if I just use check, okay, we have something like this, it is 50. Now you have a reaction happening at B because of that spring, and this, if you take the free body diagram of the spring, let us say this is my sorry let us say this is my spring RB, right? So it is going to compress the spring in this direction, and you have a reaction at RB here. So if
Yes,
you
sir.
can just find out RB, then the spring gets compressed, and that is what the support reaction is. Okay,
Yes,
so no
sir.
need to worry about what is happening, why there is a support, why there is fixed or fixed. It looks like it is fixed, but the spring is nothing but it can only resist the forces to up to certain extent in only the axial direction. It's only compression or it's compression or
Okay.
it's tension. That's it. Okay. So that is one of the condition for the spring. And now let us go ahead. So yeah, this is my let it be. So this is my beam one. This is beam one, and this is my beam two. Now only one redundant force. So what will be our compatibility condition? This is A, this is B, this is A, and this is B. So the compatibility condition will be delta 1 plus delta 2 is equal to 0. So this is delta 1, and here it is delta 2. So delta 2 is upwards. So anyways, that we need to take care while we are solving for it. So delta 1 is displacement at in beam 1, and delta 2 is displacement at B in beam 2, that is going to be equal to 0. So this is my compatibility condition.
Sir,
So let us,
I have doubt.
yeah, yeah.
Sir, why it is zero? Because sir, spring resists some force, but it is due. It is
Oh,
going
sorry. Yeah, yeah, yeah. Sorry,
function.
sorry. Yeah, yeah. You're right. Sorry, sorry. It is not zero. Correct, correct. You're right. You're right. Yeah. I kind of yes. This should be delta. Delta compression in the spring. Yeah. Pratik, you're right. So it should be delta compression in the spring. So yeah. Let us solve for it now. So what is delta one? Delta one is going to be so beam one. This is my cantilever beam. This is my 15 Newton load acting. Did I? This is 200. Okay, I didn't mention the span. This is 200 mm. Okay, so this is 15 newtons and this is 200 mm. Then the support reactions are going to be this is 50 newtons. So this is sorry, not this way. This is going to be hogging. 50 times 200 is 1000, 10,000, 10,000 Newton mm. Be careful about the units.
Yes, sir.
So yeah, now what about the BMD? Bending moment diagram will be something like this. This is my bending moment diagram. So this is 1000 by EI. Also take E as 2 into 10 to the power 5 MPa. That is for the steel. Okay. So this is my 10,000 by EI. Now delta theta 1 is going to be half times the 10,000 by EI times 200 times 2/3 of 200. This we can solve it as how can we solve this is nothing but 2 knocks off and this is by 3. Oh, you also calculate. I have given I also, right? So what is I going to be? BD cube by 12. So B is 5, 10 cube by 12. This is my I. E is nothing but 2 into 10 to the power 5 Newton per mm square. Okay. So delta 1 is going to be how much? I'm just writing it here. Delta 1 is 2000 into, sorry, 200 into 200 times 10,000 divided by 3 times all these things. So this is going to be 1.6 mm. This you can verify again. So you can just make some calculations. I have already calculated. So this I'm just writing down the answer. This is going to be delta 1 is 1.6 mm. Now what about delta 2? So delta 2 is going to be
Delta one, two into delta one, I think, sir.
2 into delta 1.
Sir, reaction.
Yeah, this is RB, right?
Yes, sir.
So it is RB, and we'll draw the bending moment diagram. RB times L. This is length L, or it is 2, or else we can just simply say 200 RB. Okay. So delta 2 is nothing but the moment of area about B, moment of area of the bending moment diagram at point B. So delta 2 is going to be half times 200 times RB times 200 times what the other one? Other part is 2 by 3 times 200 by EI. Okay. So this will be delta 2 is going to be if you substitute E and I as I told you earlier. So everything is in newtons and everything is in mm. Okay. So we don't have any issues. So we will be getting it as minus 4 by 125, something like that. Yeah, this is going to be minus 4 by 125. Why did I write minus?
1 minute, sir.
Yeah.
सर बिकॉज वो डाउनवर्ड है सर जो भी डिफ्लेक्शन है.
हाँ.
यस सर.
Yeah, in the first problem we have taken a deflection downward, so that's why we have taken its positive here. But
यस.
in beam 2 the deflection is upwards, so that's why I'm taking it as minus. Okay.
यस सर.
Yeah. So delta 1 plus delta 2, like you said, it's what it should be. It should be nothing but the compression in the spring, na?
यस सर.
So delta of compression in spring. Compression in spring. So what is delta of compression in spring? By force, let us say this is my spring. So this is RB. So what is delta B? Delta in compression because of spring, because of RB.
सर 2 into delta 1 I think.
Yeah, okay, you're saying about the stiffness. Stiffness is 2, that's why,
Yes sir.
right? Yes, yeah, you're right. So that is nothing but 2 into delta 1.
Yes sir, it is RB na.
See, stiffness is what is stiffness?
RB
Load
exam.
by RB by delta, no?
Yes sir.
Stiffness is nothing but load by displacement.
Yes
So
sir.
what is my
Displacement.
displacement? Is RB by K. है ना? RB by K.
Yes sir.
So RB by K is RB, that is nothing but K is 2, so it is going to be minus RB by K, because my stiffness again it is going to compress, so that's why
Yes
I'm
sir.
taking it as minus. Okay. But is it going to compress? That means it's going to be downwards or upwards?
Upward sir.
So upwards. No.
Reaction
See,
sir. Reaction upwards होगी sir, going downwards.
yeah, it is going downwards. So that's why we have taken downwards as positive, right?
Yes sir.
So that then it is going to be plus. Anyways, if you see what does it plus or minus, you should always be, you should always try to understand how you are going to take. For example,
Yes sir.
uh, this 50 kilonewton, this 50 newton force, it is going to make the beam bend in downwards direction. So this is my delta 1, and
Yes sir.
if this is my reaction RB, this is going to bend my beam upwards. Okay, this is my delta 2. Okay, so delta 1 minus delta 2 should be the compression in the spring. Okay, so the compression in the spring is nothing but RB by K, that is nothing but RB by 2. Are you able to follow?
Yes sir.
So delta 1 plus delta 2, the net will be the compression in the spring. So the compression in the spring is directly RB by 2. So now how can I write is delta 1 is how much? 1.6. 1.6 minus 4 by 125 RB is nothing but RB by 2. Okay. So you have only one equation, one unknown. From this you can directly find out what is RB. RB is going to be 3 newtons. Okay.
Yes sir.
So if RB is found out, if you have found out what is compression in the spring, so can you sorry, RB you have found out, that is the load in the spring. So what is the compression in the spring? Compression in the spring is RB by 2, that is 1.5 mm. Okay. So the compression in the spring is going to be 1.5 mm because of the load 50 newtons which is acting above.
Yes sir.
Yeah. So this is again this is some kind of a question which I just want to take, because in this we have a net displacement. We can't simply always, like I have done in the, when I was explaining this problem initially, I was considering delta 1 plus delta 2 equal to 0, but always it may not be true. So in this kind of questions we need to be careful. We need to
Yes
be
sir.
careful in taking delta 1 plus delta 2. There can be some support settlement sometimes. If in the question it is mentioned that there is some support settlement, then you should also then you should also consider that support settlement. So in this, it is a spring, so it compresses, and that's the reason why we have taken delta 1 plus delta 2 equal to compression in the spring. Okay. So this is
Yes.
about the question 2. So let me take one frame problem, and let me take one frame question on frames. Okay, one frame, and then we'll just. I think that will take the whole time, which is remained. So we'll just take one frame problem, and then we'll stop the session.
Yes, sir.
So any questions so far?
No, sir.
So next question. This is a frame. We have a frame something like this. This is a fixed support. Okay, UDL, and this is 8 kilonewton per meter, and this is 4 kilonewton per meter. This is A, B, C. So if you have followed the my previous sessions, I have solved the support reaction now at C. For the same question, for this question, I have solved for support reaction. But in this question, what I am trying to ask you is find horizontal displacement. So delta horizontal displacement at C, delta HC, delta horizontal at C. So just first tell me, will it have any horizontal displacement at C?
Yes, sir.
Yeah, because it's a roller, so
Yes,
it
sir.
can move in that direction, right? So yes, it will definitely have horizontal displacement at C. So take EI as constant. EI is constant, and what about the dimensions? The dimensions are, this is going to be 6 meters, and this is going to be 9 meters. Okay, so actually I have solved the same question. I think in week 6, 7. I think in week 7 I have solved the same question.
Yes,
So
sir.
for this session, what we are trying to ask is we are trying to find out delta HC. So delta HC, horizontal reaction at C. So again, I'll just solve just for the sake of completion. So I'll just solve the problem. So we have the support. We have support, fixed support. So again, what is DS? DS is going to be, we have 1, 2, 3. We have three equations here. Sorry, three unknowns here, and three and one unknown here. So total number of unknowns are 4. How many equations do we have?
3.
3. So static indeterminacy is 1. So what I'll do is I'll bifurcate. I'll divide the same beam as two different beams. With this is my R at C, and this is my cantilever. Okay. So I'm just solving the first part of the question. So that because it's already been solved, so I'm just solving it. So this is my two determinate structures. So this is A, B, C, A, B, C. So this is 8 kilonewton per meter, and this is 4 kilonewton per meter, and this length is 9, and this length is 6. So what is my support reaction going to be? My support reactions for this type of question is, this is 8 times 9 is 72. This is 72 directly, because there's only one vertical reaction that can be possible. That is possible. So what about the horizontal? The horizontal is going to be 4 times 6.
6.
That is 36 kilonewton, which is horizontal. That is the only thing which is possible. 4 times 6 is that? No. Sorry. This is 4 times 6 is 24. 24. 24. What about the word moment? So the moment is going to be 4 times 6, that is 24. 24 times 3, that is 72. plus 8 times 9 times 4.5. So put together, this is going to be 396. Okay. Now, if this is going to be RC, okay, so this is going to be RC downwards, and you have a rotation, bending moment of 9 RC here. Now, how do you find? Okay, what is our compatibility equation? This is 1 and this is 2. Yeah,
1 minute, sir.
I'll just show you. Yeah, this is my question.
Sir, vertical displacement zero रहेगा sir.
Ha, correct. Delta C, delta 1. So this is my delta 1. Delta 1 vertical at delta of vertical at C in beam
Yes
1.
sir.
Delta vertical at C for beam the frame 2 is going to be 0. You are right. So delta 1 plus delta 2 is 0. So how do you find the vertical reaction at C? Let us use the virtual work method. See, in all these, in the beam problems, it is easy. We have used the Bennett moment diagrams or the moment area methods to find it. But from this problem onwards, it's better we use the virtual work method. So for the virtual work method or the unit load method, what we'll do, we'll just assume a unit vertical load acting at that point in the direction of which we need to find out the displacement. So what I'll do is I'll just assume one. So this is my unit load 1. Okay. So this is my unit load. Because of this unit load, what happens? I'll also have displacement 1 and downwards, and this is my moment 9 kilonewton. I'm just 1 kilonewton, 9 kilonewton meter. Okay. So
Yes.
this is all it is. So this is so you use these two things to find out delta 1, and also similarly even for delta 2 what you'll do is you'll assume the same thing. So this is going to be the same 9 kilonewton meter and downwards 1 kilonewton. So you'll be using these two to find out delta 2. So from this you'll get delta 1, and from this you'll get delta 2. So I'll just write down the tabular form of what's going to happen. Okay. So delta 1 is nothing but, now you have M and M, right? It's capital M and small m. So you know what is a bending moment in this section, in this span? B and C. Bending moment in BC, it is zero, right? There is no horizontal forces. So in span BC, this is zero.
Yes sir.
Yeah. So this is small m and this is capital M. So in span BC, it is zero. Uh, what about
Sir,
yeah, yeah.
I have doubt, sir, that both diagrams are seeing. I think both have same deflection.
See, okay, it is same, but see, unit load. The reason, okay, I'll just I kind of rushed through that, but see now the concept is, sorry. So you have the loading something like this, right? This is your
Yes
initial
sir.
loading. So if you want to find the horizontal displacement, or sorry, the vertical displacement at point C, so what you'll do is you will apply you will remove the external loads. The external load is the UDL. You will remove the external loads, and you will apply the unit load in the direction in which you want to find out the displacement. Okay.
Yes sir.
So what after this what you will try to do is, okay, after this what you will try to do is you will find out bending moment in both the beams. So in both the frames. Okay. This is let us call it as uh, this I don't want to call 1 1. So what I'll do is I'll call this as 1A and this is 1B. Okay. So what you'll do is you'll first find out the bending moment in both the frames. So uh, what is your bending moment at this in span AB? Let me write like this: span, length of the span, capital M resembles to my 1A, and small
Yes,
m
sir.
resembles to my 1B. Okay, and capital M small m divided by EI dx. Okay, this will
Yes.
give me the displacement. So let me first consider span AB. What is the length of the span AB? 9 meters. What is my
9
m? So m is going to be this is 396. This is vertical 72.
minus 72x.
Yeah. So yeah. So this is going to be minus 396. It is plus 72x, right?
Yes,
72x
sir.
72x is hogging. Sorry, sagging. 72x. Okay. And do I need to consider something else? Minus 392x minus 396 plus 72x. Is there anything else to consider?
Yes, sir.
What is that? The UDL.
Yes, sir, you did.
Yeah. So that UDL is going to be minus or plus? Hogging or sagging?
Sir, sagging.
See, it is actually trying to rotate in
Sorry.
this.
Yes, sir, hogging, hogging. Sorry, sir.
Yeah. So 8 times x by 2. Okay. So this is my capital M. So what about my small m? So for my small m, this is 1 kilonewton and this is my 9 kilonewton meter. So what about my small m? So small m, can you tell me what is going to happen for small m? 9.
Yes, sir. 9 plus 1. 1 into x.
Yeah. Check carefully once again. See, you have this is 9.
9, I think, sir, downward has a 1.
Yeah, this is downwards.
Minus, yes, sir, minus.
So 9 minus x. See, if there is no plus, see, if I say no for your positive answer, then it should be minus. But it's better you understand the concepts, okay?
Yes, sir.
You are able to follow it, right? You know, the vertical reaction is downward. So, see, it is actually bending this in this way, in this downwards direction, right? So it will try to bend in this way. So if it is
Yes, sir.
going to bend in this way, that means it is actually hogging. It's not sagging. Okay. The hogging is,
Yes, sir.
see, this is my hogging and this is my sagging. So this is going to bend in this way. And what about 9? See, 9 is actually trying to bend upwards, right? So it is going to bend in this way.
Sagging.
Yeah, so that it is sagging, and the one which is going to bend is actually it's hogging. So 1 times
Yes,
x,
sir.
that should be minus. Okay, don't confuse in that. And when so this is going to be 9 minus x times minus 396 plus 72x minus 8x square by 2 is 4x square by EI. So the length is 0 to 9. It should go from 0 to 9. Now let us take BC. Length. What is the length of the beam BC?
6.
6 meters. What about capital M? So now you consider this. Now this is X. So yeah, tell me what is going to happen for BC.
Sir, horizontal support. Horizontal action.
Yeah. See, it is going to bend in this way, right? In this
Yes,
way.
sir.
So in this way, we'll assume it to be. Let us assume it as sagging. Okay.
Yes, sir.
You see from this direction, it is going to be sagging. So if it is sagging, then what is it? 4x square into, is it 4x square?
4x square by 2.
That is 2x square. Okay,
Yes, sir.
this is positive. And what is happening in this bending moment at in CB because of this unit load 1.
Sir, nothing, sir. Vertically
Yeah,
it's
it
a
is 0. Correct, correct. It is 0. So it is 0. That means that this is 0. So there is no need to take BC into account.
yes,
So
sir.
delta 1 is going to be this 9 minus x minus 396 plus 72x minus 4x squared by EI 0 to 9, and this will turn out to be minus 9477 by EI. Okay,
Yes,
so
sir.
we have obtained the answer as negative minus 9477. What does it mean?
So
That
deflection is downside.
yeah, you're right. So the reflection is downwards. Now this delta 1 we have done. Okay, what is delta 2? Delta 2 is actually the displacement because of RC applied. Okay,
Yes, sir.
so for RC is going to be your support reaction, which is redundant,
Yes, sir.
which you don't know. Okay,
Yes, sir.
so if you want to find the displacement or the vertical displacement because of unknown force RC, you will do the same thing again, right? You'll again use the same unit load method. In that also, the unit load will be acting at point C, and that too in the upwards direction.
Yes, sir.
Shall I repeat, or you understood what I said?
Yes, sir. Understood.
Yeah, yeah. So that is the reason why we are having the same unit load, the unit load or the virtual load which we are applying. Okay. So in that case, what happens is that, so this is, let us say this is the part B. First part is done. This is part B. So now we have a redundant force, something like this, which is R. How much is that? RC plus we have a unit load of 1. So we already know what is going to happen here. This is RC and this is 9 RC. This is 1. This is 1 and this is 9. Okay. So if this is 1 and this is 9, can you tell me what is A, B, C, A, B, C. So in BC you don't have any M. In BC you don't have any small m. So what is my? You only need to consider delta 2 is nothing but capital M small m by EI dx only in AB. Okay.
Yes, sir.
So what is my M? Yeah, this is now you need to tell. This
9
I
minus
already,
x.
yeah. But here it is RC, right? So 9R minus RX.
Yes, sir.
9R minus RX. And again this is 9 minus X by EI dx 0 to 9. Alright? So this
Yes,
delta
sir.
2 is going to be, uh, how much is this going to be? So you can take R outside, 9 minus X whole square by EI 0 to 1. This will be simplified to RC divided by EI.
Sir,
Okay?
can you explain again this equation 9r minus rx into
Yeah,
9 9
yeah.
minus x?
Sure. Okay. So, see, in the first, this you are able to understand, right? What we have done in this
Yes, sir.
for the in the first question, you are able to understand, right? What I have done.
Yes, sir.
Yeah. So in the second in the part B, what I'm trying to do is, okay. In part B, what I'm trying to do is, this is my M, capital M. This is my small m. Okay.
Yes, sir.
So in AB, for my capital M in AB, it is 9R. What is my at X distance X? What is my bending moment? 9R
9r minus rx.
RX. So that's what I
Yes,
have
sir.
taken. 9R minus
Yes,
RX.
sir. Understood. Understood. Yes.
Okay, something like that. So this delta 2 is 243 RC, and it is also upwards as I Assume the upwards to be positive, so it is upwards. Now, delta 1 plus delta 2 is equal to 0. Delta 1 I have found it as 9477 by EI plus 243 RC by EI. That is going to be 0. Okay? Just a
Yes.
second, I'll just a minute, I'll just have some water and will come. Just a minute.
हेलो करीम भैया। हाँ बोलिए। मैं थोड़ा क्लास में हूँ भैया, तो 9 8:40 थोड़ा 10 15 मिनट रुक सकते हैं क्या आप? हाँ हाँ हाँ। अम, हाँ। नहीं नहीं वो, हाँ वो 2.5 डालेगा। हाँ हाँ बताएं। नहीं, आप थोड़ा 15 मिनट रुक सकते हैं क्या? मैं क्लास में हूँ, मैं अभी, आप, मैं क्लास होते ही मैं कॉल करता हूँ, रुकिए आपको। हम्म।
Yeah. So,
So
yeah, this
you will get RC
you will get
is nothing
RC
but
is
39.
nothing but 39
Okay.
kilonewtons. Okay.
So now
So now
Yes.
you have
the
obtained
support
the
reaction
support
RC.
reaction
Now
RC.
once you have
Now
obtained
once
the
you have
redundant
obtained
force,
the
now you can
redundant
find
force,
out
now you can
the
find out what are the
other forces.
other forces. So how do you find the other forces?
This is my
So this is my question again.
this is
This is my
RC,
RC
and RC
and RC we have got
RC is
RC
39
is 39 kilonewtons.
what about
What about we have a
UDL?
UDL 8 kilonewton per meter. So
8
8
kilonewton per
kilonewton per
meter.
meter is my UDL, and this is my 4 kilonewton per meter. So if this is 39,
So this
so
has to
this
be
has to be 33 because the total is 72,
and this
and
will be
this
for
will be for
24
24
kilonewton
kilonewtons,
kilonewton
kilonewtons,
kilonewton.
kilonewtons,
And
and this is going to be 45 kilonewton meter.
okay, this you can
Okay, this you
verify.
can verify.
So now we have
So now
Yes,
we
found
have
sir.
found this using the compatibility conditions.
now what is the
Now what is
question?
the question? The question is
Now find
now
out the
find out the
horizontal
horizontal
displacement at
displacement
C.
at C.
A,
A,
B,
B,
C.
C.
So now you tell
So
me
now
how
you
to
tell me
find
how
out
to
the
find out the
horizontal
horizontal
displacement at C.
displacement at C.
What we need to
What
do?
do we need to do?
So just adding both good displacements.
Yeah.
Yeah.
So
So
adding both
adding
displacements.
both displacements.
No, you can use
No,
unit load
you
method.
you can use
Sorry,
unit
sir.
load method in this. So for yeah
Yes, sir. I'm just.
Yeah. So
yeah. So
maybe I can
yeah,
explain
maybe
you.
I think you have understood it, but you are not able to tell me. So
This is something like
Yes,
see,
this.
this
sir.
is something like this. So you
So
have
this beam,
this
you
beam.
have
You
already
have
have the
you
support
already have the
reaction,
support reaction at this,
and you need to
and
apply
you need to apply
unit
unit
unit load one
unit load
in the
one
direction
in
of
the
which
direction
you
of
are
which
asked to
you are
do that,
asked to
right?
do that, right?
So
So
for you the question
for
is
you the question is
what is
what
the
is the
horizontal
horizontal
displacement
displacement
at C?
at C?
So for that
So
what you
for
do
that
is
what
you
you'll do
apply
is
a
you will apply a
horizontal load
horizontal
of
load
1
of
kilonewton
1
at that
kilonewton
point
at
C,
that point C,
and
and you find out
the
the
displacement at that.
displacement at that. So
Now the
now
question
the
itself
question
again
itself again
in the
in
solution
the
itself,
solution itself, now this is going to be an
uh,
interesting one, right? So
first thing
first
is
thing is
this is your
this is your
main
main
question. This is
question.
your
This is
main
your main
question,
question, or let us say this is your
capital M,
capital M,
and this is
and
going
this
to
is
be
going to
small
be
m.
your small m.
So
So
now tell
now
me
tell
in
me in
small m
small m
itself is an
itself is an
indeterminate structure.
indeterminate structure, right?
So now
So now
Yeah.
the
for
so
that
for that
indeterminate structure,
indeterminate
you need
structure,
to
you
find
need
out
to
the
find out
support
the
reaction.
support
To
reaction.
find out
To
the
find out
support
the support
reaction,
reaction,
again
again
you
you
need
need
to
to remove that
remove that
support, and
support.
you need to find you need to do the compatibility equation, and then you need to find out the support reactions for this.
You're able to
You're able
follow?
to follow?
Yes, sir.
Yeah.
Yeah.
So
So see in this
let's say
let me say this is my frame.
let's
Let's
say
I'll
this
say
is
this is
frame
frame
one.
two and this is my
This is frame one.
frame one.
So in
So
frame
in
two,
frame two, now the frame two, the problem is
already
Frame 1 I have
solved.
already solved. Okay, in frame 2,
Now my
now
load
my
is
load
one
is 1
kilonewton
kilonewton
acting
acting
here.
here.
But if
But
you want to
if you
find
want
out
to
the
find
bending
out the
moment,
bending moment, bending moment equations, right? Like we,
as we are
as
finding
we are
earlier,
finding earlier, we are finding out what is small m, right? 9 minus x, whatever it is. But here you can directly say it is 9 minus x or something, because this itself is an redundant, indeterminate structure.
Yes,
So
sir.
initially you need to remove this. So this can be solved in this way. So this can be. I'm just writing it. I'm just scaling it down and I'm writing it down. So this can be solved in this way: the 1 kilonewton plus
again RC.
again RC.
Okay,
Okay.
you are able to
You are able to
follow.
follow.
Yes, sir.
So one
So 1
kilonewton
kilonewton
horizontal
horizontal
direction
direction,
and
and RC is my redundant force.
so
So what is my compatibility condition again?
delta
Delta
C1
C1
plus
plus
delta
delta
C2
C2
equal to
equal to
0.
0.
So I'll
So
find
I'll
my
find my
delta
delta
C1
C1
in
in
this
this
and
and
delta
delta
C2
C2
equal
equal
to
to
0,
0,
and then I'll
and then
find
I'll
out
find
what
out
is my
what is my
RC.
RC.
Okay.
Okay.
So
Yes, sir.
So
I'm just
I'm
writing
just
it
writing it
down.
down. Maybe
You can
you
go
can
back
go
and
back
you
and
can
you
solve
can
the
solve
question.
the question.
So
So I'm just
Yes, sir.
writing down what is my RC in this condition.
So this is
So this is my beam.
this is
This
one
is 1
kilonewton,
kilonewton,
and my
and my
RC is going
RC
to
is going
be
to be my RC is going to be. Did I solve for it?
yeah. I
Yeah,
think
I think RC is going to be
three times
3
three.
times 3. Yeah, it's going to be 1.
Yeah.
Yeah.
So
So
in this
in this
case,
case,
my
my
RC is
RC
going
is
to be
going to
one
be 1
kilonewton.
kilonewton.
Okay.
Okay.
So if it
So
is
if it
one,
is 1,
so
so
here it
here
should
it
be
should
one
be 1
kilonewton,
kilonewton,
and this should
and
be
this
one
should be 1
kilonewton,
kilonewton,
and
and
my
my
reaction
reaction
for
for my bending moment
is
is 3
3 kilonewton
kilonewton
meter.
meter.
Okay.
Okay.
So now
So
coming
now
back to
again, coming back to our main question.
the main
The
question
main
is
question
this.
is this.
So you
So
have
you
a
have a
beam.
beam,
Sorry, you have a
sorry, you
frame.
have a frame.
This is
This
your
is your
frame.
frame. This is my frame. What are the support reactions? We have already found it out. This is 30.
This is my
This is my
39,
this is 39,
and
and this is 33.
this is
This is
24,
24,
and
and sorry, not this way.
this is
This
45.
is 45. Okay.
So this is
So
my
this is my
the question
the
is
question is
to find
to
the
find the
horizontal
horizontal
reaction at
reaction at
the
the
horizontal
horizontal
displacement
displacement
at
at
joint C.
joint C.
So for this,
So
what
for
we have
this,
done,
what we have done, we have taken the same beam,
we have
we have
applied
applied
we have
we have
applied
applied
unit
unit
horizontal
horizontal
force,
force, unit
unit
horizontal
horizontal
force at
force at
joint
joint C,
C,
1
1
kilonewton,
kilonewton.
and
And
for
for
this
this
force,
force, like, see,
this is 1,
this is 1
this is
and
2.
this is 2.
For
For
frame 2,
frame
we have
2, we
also
have
solved
also
for it.
solved for it, right? We have also solved for it.
So we
So we
solved
solved
frame 2.
frame 2 because it is again an indeterminate structure, so we need to solve for it. 1 kilonewton, and this is going to be 1 kilonewton. This is going to be 1 kilonewton, and this is 3 kilonewton meter.
Now
Now we
we have
have
all the
all the
support
support
reactions which are
reactions which are
required for us
required
to
for us
solve
to solve horizontal displacement.
So this
So
is
this is
capital M
capital
and this
M
is
and this
small
is
m.
small m. Let us again
Write it
write
down.
it down. Let us again write down
Or
or
tabulate
tabulate
all the
all
values.
the values.
So
So
we have
we have
span,
span,
the length
the
of the
length of the
span,
span,
capital M,
capital M,
small m,
small m,
integral
integral
delta
delta
capital
capital
M,
M,
small m
small m by
I
EI
dx.
dx.
Okay.
Okay.
So
So
first span
first
AB.
span AB.
I did not
I
mention.
did not mention.
A,
This is A,
B,
B. Okay, already I mentioned A,
C, D,
B,
C.
and C.
So for
So for
AB,
AB,
yeah, what is
yeah,
length?
what is length? Length is 9.
Capital M
Capital M, what is capital M?
So capital M 100
Yeah.
Yeah,
Minus
minus
45
45
minus
minus
45
45
plus
plus
33x.
33x.
Is there
Is
anything
there
else?
anything else I need to add?
yes sir UDL
Yeah,
Yeah,
UDL.
UDL. How much is that?
sir 8x square by 2
Is it
Is
plus
it
or
plus
minus?
or minus? Think
Think
carefully and
carefully.
tell me.
100 sir
Yeah.
Yeah,
So
sure. You can take your
plus
time. Just tell me whether is it plus or minus.
minus sir
30.
minus. Yeah.
Yeah, absolutely right. So it is minus 4x to x square.
Okay.
Okay.
Now what is
Now
small
what is
m?
small m?
Similarly,
Similarly,
this is
this
x.
is x.
so 3 minus x
Yeah.
Yeah, wonderful.
So
So yeah, this is going to be
minus
minus
45 plus
45 plus
33
33x minus 4x squared
multiplied by
multiplied by 3
3
minus x
divided by
divided by
I.
ei.
Now, what is
Now,
the other one?
what
Span
is the other one?
BC.
Span BC.
See, the reason why I'm
See,
not
the reason
taking
why I'm not taking
from end
from
B,
end B,
because
because
see in B
see
we
in
already
B
have
we
some
already have some
you
you at
the
see
rigid
at the
joint.
rigid
B
joint.
is an
It's B is a
integral
rigid
joint.
joint, right?
So
At
rigid joint
rigid
means
joint
yes sir
B,
you'll have
you'll
some
have some
movements and
movements
also
and
you'll
also
have
you
some
have
shear
some shear
forces.
forces.
So
So
if you
if you
want to
want to
start from
start
B,
from
right?
B, right, you need to consider all these
That
things.
again
That
that will
again
be an
that will be an
extra
extra
time for
time for
calculation. So
calculations.
that's
So
why
that's why
the
the
easier part
easier
is
part is
I'm
you
taking
I'm
it
taking
from
it
the
from the
C
C
from
from
support
support
C
C
because
because
at C I
at
yes
C
sir
I
already know
already
the
know the
forces.
forces.
That is the
That
only
is the
trick.
only trick. Okay.
So
yes
So
sir
for the
BC the
BC
length
the
is
length
6
is 6
meters.
meters.
Tell me what
Tell
is
me what is
M.
M,
Capital M.
capital M. So
sir
this is
Going to bend like this.
4x
going to bend
square
like
by 2
this.
4x
4x
square by
square
4x
by
2.
2
square
4x
by 2
square
4x
by 2.
square by 2.
But see,
But see, I told you right.
this is
This
going
is
to
going to
bend
bend
like
like
this.
this.
So
So
let
let
us
us
assume
assume
this
this
to
to
be
be hogging.
okay.
Okay.
yes sir
So that is
So
minus
that is
2x
minus
square.
2x square.
And what about
And
small
what
m?
about small m?
small m sir 1 minute x sir.
X but
X, but
this is
again,
going
this
to
is
bend
going to
like
bend
this.
like
Minus
this.
x. Yes, sir. Minus x.
So
So both are
so
actually
both are
going to
actually
be in
going to
that
be in that
direction. So
direction. So
minus x.
minus x. Okay.
And this will
And
be
this will be
minus 2x
minus 2x square
minus x
minus x
by EI.
by EI dx.
Okay.
Okay.
Now your
Now
delta
your delta, actual
delta
delta
horizontal
horizontal
at C
at
is going
C
to
is
be
going to be
minus
minus
45 plus
45 plus
33x
33x minus
minus
4x
4x
square
times 3
times
minus
3
x
minus x dx
by
by
EI
EI
0 to 9
0 to 9
plus
plus
0 to 6
0 to 6
minus 2x
minus 2x square minus x, again that will be plus.
so
So
delta
delta
HC
HC
is going to
is
be
going to
if you
be,
solve that
if you
you are
solve
going
that,
to
you are
get
going to get
243 by
243
EI
by EI plus
648 by
648 by EI.
11
11 4489
9
629
891
891 by EI
is going to be in this
is going to
direction.
be in this direction.
So the
Okay.
roller
So the
support,
roller
Yes, sir.
support which we have,
so the initial
so the
roller
initial
support,
roller support,
the
okay,
initial
the
roller
initial
support,
roller support,
this
this
support is
this
going to
support is
move
going to move in this direction
by a distance
by a
of
distance of
891 by EI.
891 by EI.
Okay.
Okay.
So
So this is
the
what I want to discuss for
today's class.
today's class.
Uh,
Uh,
anyways, you can
Anyways,
also
you
see
can also
we
see we
have
already have
the
the
support reactions,
support
right? So
reactions,
we
right?
have
So we have, what is this? This is
33,
33.
this is
This is
39,
39. This
this is
is 24,
24, and
and
sorry,
sorry, this is
45.
45.
Okay.
Okay, so you already have support
Yes, sir.
reactions, so you can also find shear force bending moment diagrams, right?
Yes, sir.
I'll just maybe I can just show one shear force diagram. So here it is 33. Okay, so what is going to happen at this support? Oops, what is going to happen at this support B? Shear force at B is going to be 33 minus 8 times 9. That is nothing but minus 39. 72 minus 33. Yeah, 13 minus 39. So if it is plus in this in this and here it is going to be, this is 33, so this is minus 39, so somewhere here, so this is going to be something like this. This is my shear force diagram. And
Yes, sir.
what about at B? So at B,
24.
uh, yeah, constant, right?
Yes, sir.
So it is 24 here, and then when it comes to this, it is going to be 0. Yeah, this is 24, 33, and this is minus 39. Positive, negative. Let me take this as positive. Similarly, you can also find out. You can also draw the bending moment diagram.
Yes, sir.
Can you draw it or
Yes, sir, I can.
you can? Okay, fine. Okay. Do you have any doubts or you want some clarifications or you want?
Sir, you just find in frame M where,
Yeah.
सर
Yeah.
हॉरिजेंटल सपोर्ट था सर, आपने डायरेक्ट जो 3 किलो न्यूटन मोमेंट लिया था,
Ha
यस
ha
सर
ha.
यही बात है, यस सर ये।
Ha ha. Okay, I understand. I understand your question. So, see, the thing is, see, if you want to find the horizontal support, see, the question is you want to find horizontal displacement at support C, na?
यस सर।
So, if you want to find, see, what is our virtual work method saying? The virtual method says that wherever you, if see, for example, if you want to find horizontal displacement at support C, for the same beam, you remove the external loads. So the external loads is nothing but the UDLs.
यस सर।
You remove the external loads, and for the same beam, you apply unit load in that direction of the horizontal load.
यस सर।
Okay. So what I have done is for the small m, I have applied 1 kilonewton at support C. If for example, if you are asked to find the horizontal displacement at B, okay? So if you are asked to find the horizontal displacement at B, then what you will do is instead of applying horizontal displacement at C, you will apply horizontal displacement at D. So then this will not be there.
यस सर।
Okay. So now because of that, what is happening is this itself is again becoming a, see, now you can see this itself is again becoming
इनडिटरमिनेट।
yeah, indeterminate structure. So for this again you need to find out what are the horizontal what are the support reactions. So like we found out for the first one, right? Like if you remember the first question is this like this is our, we started with this question.
यस सर।
So for this question what we have done, we have removed this support C, and then we have applied RC as a redundant force, and then we have made the compatibility condition there. Correct?
यस सर।
So in this also we again to find out the horizontal displacement, we are applying unit load at support C, which is 1 kilonewton. Again that is acting on an indeterminate structure. So for that again we need to find out the vertical reactions or the support reactions.
यस सर।
Okay, so this will be, this is this question or this box. Okay, I'll just maybe let us say this is frame 2. This is another question again, this is the similar question, but in this you only have a point load 1 kilonewton, whereas in our first question we have a UDL of 8 kilonewton per meter and 4 kilonewton per meter.
यस सर।
Okay, so this is something like that. So I just don't want to repeat what I have done, that's why I have directly given you the answers. So
Yes, sir.
yeah, initially we are getting RC as 39, right?
Yes,
So
sir.
when you are applying the unit load at that 1 kilonewton of unit load, you will be getting your RC as 1 kilonewton. Likewise, you can find out this 3 kilonewtons and 1 kilonewton, 3
Yes, sir.
kilonewton meter and 1 kilonewtons. That I have directly given. You can just confirm this. Okay, you just go back and you can work out the same question. For
Yes,
this
sir.
question, you just find out a delta C. Delta C because of you remove this support, you give RC. Okay, and you find out the delta C. So delta C1 plus delta C2 should be 0. From
Yes,
that
sir.
you can find out RC again, like how we have found out here, right? 39 kilonewton.
Yes, sir.
In the similar terms, you can find out RC there. And once you find out that, you right now now you have everything. Like you have applied 1 kilonewton horizontal force. You know what are the support reactions. Why do we need to know support reactions? Because we need to know what is my small m. For small m, you actually want to know the support reactions. Only from if you know the support reactions, only then you can derive your bending moments, right?
Yes, sir.
So that is the reason why you found out the support reactions. From support reactions, you formulate your small m and capital M, and once you found out those small m capital M, you will be using this integral capital M small m by EI dx to find out your delta Hc or the horizontal reactions or the horizontal displacement.
Okay, sir.
Okay. Anything else?
Sir, there is any group for this? If I have any doubts.
You can actually ask in the forum, right? Or you see if you have questions in regarding uh, like if you have questions regarding the session, right?
Yes, sir.
You can like you have the links, right? You have links for